Hi everyone, my name is Nick and welcome to this first episode of This Week in Architecture. And this is going to be a series where we go over a recent publication at a top conference in computer architecture or a related field, and we try to summarize that paper. That way, you guys can better understand what are the, current hot issues within computer architecture and computer engineering without having to dig through an entire, the entire sea of papers out there and then having to read an entire paper you may not understand. So in this case, we'll be looking at this paper, Parties, QoS-Aware Resource Partitioning for Multiple Interactive Services. And this is to premiere or to, it will be published in ASPLOS 2019. And ASPLOS 2019 is architectural support for programming languages and operating systems. So while not a direct computer architecture field, it does have a lot of architecture in the conference, as well as a lot of more software type things. And this is one of the more software type papers that gets published there. And it's from a lab at Cornell University. And let's go ahead and get started with our presentation. So let's start out. So let's give an overview of what the paper tries to tell us. So the main key point is that modern data centers lack or limit co-locationcy of latency critical tasks. So a latency critical task is one that we care about when it finishes. So what this does is it limits efficiency. The less we can move tasks around and group them together, it becomes harder to efficiently use our resources because we may be under provisioning in some places and end up, because of the under provisioning that we have to do because we can't co-locate things, we may also over provision or we may oversubscribe resources to a specific process. So, say a latency critical task gets, a ton of memory and cores that it maybe doesn't need, but this is just to make sure that no one else can interfere with it. So in this case, we're wasting a lot of resources. Now, the other thing that this paper points out is that there's an increasing number of jobs that are latency sensitive. So this isn't just a current issue, it's a growing issue. So what do they propose? So they propose a QoS, which is Quality of Service, resource manager called Parties, and the way that Parties works is through dynamically adjusting resources to meet all deadlines. So when we talk about quality of service, we're talking about a specific application that has to be done by a certain deadline. And that's what this quality of service really stands for. So we want to be meeting deadlines. So let's look at some background in the area. So there's a number of methods for handling interference between multiple applications. So the most obvious one is to just disallow sharing. So you say that some latency critical task goes on this hardware and nobody else can be co-located with it. Now, this is obviously going to make sure that your application can meet all its quality of service deadlines because there's no interference. However, you have the problem of you're giving it too many resources that it doesn't need, and you could potentially stack more applications running concurrently or co-located with that particular latency critical application, and you better utilize your entire cloud. So what else can you do? You can just avoid co-sharing applications with likely interference. So you may know ahead of time that you have a certain memory-intensive workload that you may not want to put with another memory-intensive workload. So you just say, even though these are both these potentially could go together, they're both memory sensitive, so don't put them together. So this is another constraint on this area of scheduling. So again, while not as bad as not completely disallowing sharing, you're still limiting the amount of sharing possible. And then the last and one of the strict things you can do is also partitioning resources. So you say that, this subset of resources is allocated for this process, and only this process can allocate use those resources. Now, this is another dynamic allocation system. In previous works, it mainly focused with you have a single latency critical application, and then another one where latency was not critical. So in this case, you can provision resources for the latency critical task. take away resources from the non-latency critical task, but it doesn't address this issue of what if you can you get away with running multiple latency critical tasks together while still meeting QoS deadlines. So what about some application trends? So there's a shift from batch jobs to low latency services. So when we're talking about batch jobs, batching is when we take a whole bunch of different applications we want to run or tasks that we want to run. We group them together. We wait until we have a certain number called our batch size, and then we send it out to get executed or processed. Now, in this case, we really latency is less of an issue. We're mainly trying to optimize for throughput, so we want to make sure that we have enough work to fully saturate a machine, and then we send it out then. But with latency, low latency kind of tasks, we don't just care about the throughput of the machine. We want to make sure that the tasks are getting done quickly, not necessarily as fast as possible, but fast enough to meet its deadlines. And then we also have this common trend of large applications being split into microservices. So you can think of a large application being instead a number of smaller applications. And those small microservices may have more strict latency deadlines. Okay, so let's talk about the characterization for a little bit. So we have to, when we're doing research on a new way to schedule things or to allocate resources, what are we allocating resources for? So the applications that they use are a memory object caching program, one that's a web search engine, one that's a high-performance HTTP server, a program for statistical machine translation, a NoSQL database, and then speech recognition application. Now, a lot of times when you have these applications, you want to make sure you get a good variety of applications. So here, from the paper, they show that not only do they have 6 different applications, they all have various different features about them. So some of them have higher IPCs than others, such as between web search and this database software that's really I/O heavy. So because it's I/O heavy, it ends up having a lower IPC. And then also they differ in the amount of, say, misses they have in their last level cache. So here they have misses per 1,000 instruction, as well as they show that they have differences in the amount of disk bandwidth, memory bandwidth, the overall memory capacity they use, and the network bandwidth that they eat up. Okay, so let's talk a little bit about resource isolation and mechanisms. So there's a number of different mechanisms to do this resource isolation that exist today. So as far as core isolation goes, they tackle this with the Linux CPU set C groups, where they can allocate specific cores to a given application. For power isolation, they use a user space governor to take a selected core and to fix it at a certain frequency. Oops, there we go. So then they have, for the cache allocation to a specific process, they can use what's built in with Intel's cache allocation technology, and they can do that for way partitioning in a cache, so they can say that these particular ways of a cache will belong to, say, this program, and they're exclusive to that program. Now this is also a way of, it's a proxy for also limiting memory bandwidth, or it regulates it indirectly, as they mention. The reason why it does that is because if you hit in your cache, if you make an access to a cache and you hit in it, you're not going to generate a request that has to go out to memory. So as kind of a proxy, if you make the cache bigger, you're going to decrease the amount of memory bandwidth that you're going to need. And the opposite of that, if you make a cache smaller for a certain process, you increase the likelihood that it's going to miss in the cache and need more memory bandwidth. So it's kind of a balance game there. Then, of course, we have memory isolation and disk isolation, and then network isolation that we can do as well. Okay, so let's talk about some application limitations. So they do this study here where they run each of these applications with their max load, which is the maximum, with the maximum number of requests per second that they can handle, while still meeting all of their quality of service deadlines. And over here, they run it with another application that is, they run it with another application that specifically has interference or that causes interference. So they want to measure the impact of resource interference. So let's take, for example, MongoDB for all of these different parameters or resources that they want to partition. So in the case of MongoDB, it does pretty well for most of the different resources as far as it's able to maintain near 100% max load without missing any quality of service deadlines, except for memory capacity and disk bandwidth. In the case of memory capacity and disk bandwidth, in a contentious scenario, it has to reduce down to only 10% of its max load in order to guarantee that it's still making deadlines. And then you also have Memcache over here that, it's sensitive in a lot of different areas. So in high contention scenarios, things like last level cache bandwidth, hyperthreading, CPU, all of these resources, the maximum percentage of max load that they can satisfy this QoS when there's when it's running under interference is 0% for a lot of these categories. So this just kind of goes to show that this is a very important thing, that we understand how different resources affect a specific program's execution and how it can change, how it can meet deadlines. So let's look at a quick sensitivity analysis that they do. So in this way, they're looking at allocating cacheways and how different applications are sensitive to, say, just a very high memory usage micro benchmark. So micro benchmark is just a small benchmark that's used to exploit maybe a specific feature, and in this case, it's generating a lot of memory traffic. So in here we have on the x-axis the number of cacheways that are allocated to the application, and then the number of cores. And we see that with all cases except for MongoDB, all of these are sensitive to low number being allocated a small number of cores, where this X on this heat map indicates that it's unable to meet quality of service deadlines, even at the being allocated, say, all the cacheways. Now, then they show it at a low load of 30% of the max load, and showing that there's a lot of opportunities in order of different ways, or different number of cacheways that an application can be allocated, and a different number of cores that they can be allocated in order to still meet deadlines. So there isn't just one fixed point. They don't all need all the cacheways and all the cores in order to meet their quality of service deadlines. They just need to make they could be at any of those points and make the deadline. And then the heat map represents the frequency of the cores. And so here in this last one, they show that if we have a low load and while running with a memory, this memory thrashing benchmark. So we see that some applications do better than others. So in the case of Memcache, even under this thrashing micro benchmark, we get it's going to require a couple more cores, but overall there's still quite a few opportunities where this can meet all quality of service deadlines within the parameters that they select. But then we look at, say, Moses, for example, and we see that while still at a low load, if it has this heavy memory intensity micro benchmark running, our area that it can still meet all its quality of service deadlines becomes extremely limited. As you can see, the number of X's grow extremely, almost to the point where under contention, it's almost like it's running under a 90% of the max load. Okay, so let's talk about their actual design of parties. So it's resource allocation. So they want resource allocation to be dynamic and fine-grained, which means they don't want to just block allocate giant amounts of resources. They want to be a little smarter with it and allocate what is needed, not to oversubscribe too much. They also want to assume that they have no a priori application knowledge or profiling. So they want to assume that you could run any application on the system and it would find a solution for you. They also want to make sure that there's fast recovery in case you make a poor decision in terms of partitioning, and that if we need to move a task to, say, a different area, that's a last resort. So we really want to make sure that, we really try out our search space for, how we're allocating all of these different resources before we decide to do a really, really expensive task like moving an application out and all of its accompanying state out. So let's talk about it a little bit more. So the controller itself. So what do? So when two applications, say, are running together, or multiple applications, what they say is that to start out, since we don't know anything, the safest thing to do is to just equally partition the resources. Then they sample every 500 milliseconds how much or what are some of the statistics about the application. So how fast is it running? What is the bandwidth that it's using as far as memory goes? How many misses is it getting in the cache? And what it's going to do is it's going to make adjustments based on tail latency slack. So this is if a program is completing really, really quickly, that means it's been given too much or too many resources, so it can downsize the amount of resources it has. And then if it's low or negative slack, meaning that it's either missing deadlines or will miss deadlines, you can upsize it, meaning give it more resources. And then, of course, they track how long QoS violation has been occurring. And the reason why they do this is maybe there's not a solution in the system. So if you have, a bunch of, say, really, really big applications that are running near max load, and you have another application in there, there may not be a specific space where that application can still meet its quality of service deadlines. Or in some cases, it may be a very narrow area of resource allocation where it can, and that may be just too difficult to find. So they time this in order to see, this application has been missing too many deadlines and it's continuing to miss. Take it out, move it someplace else. But like we said, that's a last resort. Okay, so let's talk about the design of the controller some more. So the first thing we do, so how do we know which resource to change? Because we don't necessarily know, because we're not doing any offline profiling of the applications. We don't know if it is super cache intensive app. We don't know if it's something memory related or disk related. So what they do is they pick a resource at random, and what they do is they will increase that resource by a fixed amount, and then they will wait for another sample, and then they'll check the latency and see if it did any better. Now, they need to be careful here. So if they're really bound on memory bandwidth, if they increase memory bandwidth, they'll get some immediate results. However, if it's something more compute related, so in this kind of state machine over here, you're not necessarily going to see the results right away. And the reason is you could have a lot of things queued up in buffers, and you're not going to see results as far as forward progress until you start draining all the buffers that have been filled with pending work for quite a while, potentially. So continuing on with this design of the controller. So how do they select a victim to, say, take resources from? So the first thing that they need to avoid is out of memory errors. So they don't want a program to exit because it gets an out of memory error. And then the other thing that they don't want to do is they want to avoid ping-ponging between multiple upsizing applications. So you may have two applications that are missing deadlines that are co-located with each other, and you want to make sure that both state machines, say, aren't both trying to get, say, more ways in the cache, because this guy may ask for more ways and take ways away from this guy, but then this guy may be in the same part of the state machine and take ways away from the other guy. So they want to avoid that. So what they do is that in these situations, they'll just cycle to a different state in the state machine, and they'll try to optimize or try to increase resources in another area. And then, of course, if there's a non-QoS application, so one that doesn't have an explicit deadline, that'll, of course, be the first victim that they pick. So what are some of the questions that they also address in the discussion? So what does parties need to know? So the only thing parties need to know is in the case of that memory of that out of memory scenario. So they need to know only if a job is really capped on memory. And what they do is, what they do is a second of profiling at the beginning of application execution, where they get a measurement of how much memory this application is using. And they'll use that to know if this application is capped and really we can't decrease memory from it. But other than that, we don't need any other knowledge about cache, miss rate, hit rate, information about the application as hence. We'll find that out at runtime through our profiling. So how do we monitor latency? A lot of these applications have built-in monitoring systems. And the ones that don't have built-in monitoring systems, even if they're running in a cloud scenario, oftentimes they provide probe points for a cloud service to probe into and collect these statistics and give it back to the person running the program. So how do they determine the controller's parameters? So a lot of them are kind of heuristic based. So they go, we want to make sure that we're not, taking away resources too quickly and not letting them have an effect. So they say, 500 milliseconds for sampling is a good balance for this. And they do this for all their parameters. Say, how much memory bandwidth to increase or decrease on an upsize or a downsize. And then the cost of upsizing on other applications. So that's something that they had to consider as well. So they need to make sure that if an upsize hurts a downsize, this naturally will balance itself out, because if that downsized application is suddenly missing QoS deadlines and has the smallest or negative slack, then the next time it comes around for optimization, it will grab new resources. So it's a self-balancing system. And again, we talked about job migration, how that timer to keep job migration to a minimum, and then job scheduler influence. So you have another scheduler out there that's giving jobs to the system, and what they say is that with their system, they can provide hints to the job scheduler to say, hey, don't send me any more jobs don't send any more jobs here because I'm having trouble already with these jobs. So don't give me too much work to do or even more work, because then everybody will start missing deadlines. And then you also prevent job migration from needing to happen, because you ensure that a job that won't make its QoS deadlines never gets into this, or will ever get into the system. So let's talk about some of the results. So as just kind of a early exploration, they just ran each of the 6 programs with each other, and they plotted out the max load that they were able to attain while being ran with each other. So this will be Memcache with all the other applications, down to MongoDB with all the other applications. So more interestingly, they show a comparison against other state-of-the-art ways of doing this. So in this case, they have it being unmanaged. They have another research one, Heracles. And then they have parties, which is theirs, and then they also have an Oracle system. So this is going to be a Oracle. When we talk about one that's Oracle, we're not talking about the company. We're talking about a system that has perfect knowledge, or it knows everything about the system. So again, like we said, parties doesn't know anything about the application. With something like Oracle, we're assuming that it's the best possible solution that we can come up with. And so we see that parties does a very good job compared to all of these others, and even gets close to the ideal Oracle performance in terms of what percent of max load can be attained when running multiple applications with one another. So then they do another example. So in the previous ones, in a lot of the previous other examples, they assumed that, say, resources or a certain application would be fixed to a certain level. So in this case, we're talking about 20% of max load or 30% of max load. But then they also test it as far as, what if that max load changes over time? How do these different systems adapt, or how do they work? So in this case, they run these three programs together with a varying max load, which this percent of max load is up here. So memcache, kind of steps up all the way to around 60% before stepping back down. And you see that here's the normalized latency of these applications, with the starred line being the QoS deadline. And we see that for all three applications, Parties does a pretty good job at staying under this QoS deadline. While we look at the two other applications other than memcache for both the unmanaged case and with Heracles. So Heracles, after it starts stepping up to a certain point, two of the applications just never make their deadlines anymore. They jump off here to off the graph, and then even here in this unmanaged scenario, memcached misses for this entire section. While over here we've got some jitter on all of these lines going up and down over this quality of service deadline. And then they show that what are the cores and what are the frequency and what are the last level cache ways to get allocated over time for these three applications. So all of these steps correlate to those resource allocation tuning things that happen that they mentioned in the paper. So this is a visual representation of that. Okay, so what's the kind of conclusion of this paper? So biggest thing is they outperform the state of the art. So they got an average of 61% increase in their ability to make quality of service deadlines, or rather, I believe it was a 61% improvement over resource utilization and being able to make these quality of service deadlines. And so the way that they did that, like I said, is they're able to pack multiple latency critical applications together on the same hardware instead of just having one. So then they, again, it allows multiple latency critical things to be co-located, like I said. It leverages current isolation mechanisms, so they don't need to do anything new there. They're utilizing the allocation things that are already in the system. And then they settle, the best thing is with quality of service, it's important to realize that they're just settling for an acceptable solution. When it comes to quality of service, we're saying that we need a task done by a certain deadline. We don't get bonus points if we finish the task early. We just care if we make the deadline every single time. So while the search base gets incredibly large for once your number of applications gets to be 4, 5, and 6 located together, and finding that balancing point for the 8 different resources that they manage, they say that in reality, while the search space overall is very large, we're not trying to find the optimal solution, just a working solution. And that heat map plot that we looked at earlier showed that everywhere that wasn't X'd out, that is a viable solution for that architecture. Doesn't matter which one we pick, as long as it's viable. And these violin plots here show that between 2 and 6 applications, the time that it takes to converge to a specific or to a solution that works for all these applications, it really only increases by about 2x once you get to 6 applications, so about 1.8 to 2x. So, considering you have 4 more applications on that node now, that's not really a large increase in time in order to find that optimal point, especially if these applications are running for, multiple minutes, potentially hours, right? So this is a very nice thing. So like I said, this is Parties, this QoS resource partitioning for multiple interactive services paper from ASPLOS 2019. Let me just make sure on that. So yeah, so they improve throughput under QoS by 61% on average. So that's saying that the amount of work they're getting done while maintaining QoS improves by 61% over existing resource managers. Okay, so all of this content, these slides, will be available under the github.com/coffeebeforearch page. And if we go to TWIA, that stands for This Week in Architecture, we're going to have both links to the papers that are available for you guys to read, as well as links to the slides that we presented today. So feel free to check these out. Let me know if there's a specific paper that you might want to have covered here. Send me an email. I would say make sure that it's something that's more architecture related, as this series is about computer architecture, but there's plenty of papers that I have already lined up that we can go over. So thank you guys for watching, and I hope you have a nice day.